Have you ever stopped to think about the camera in your pocket? We're going to trace the incredible story of how we went from a clunky box that took ages to snap one blurry photo to the supercomputer you carry around every day. It's an amazing journey through chemistry, silicon, and, honestly, a little bit of computational magic. Let's dive in.
So, it all starts with this one big question. How on earth did we get from a piece of hardware that was, let's be honest, ridiculously clumsy and painfully slow? And you're looking at it right here. This was built by a Kodak engineer named Steven Sasson back in 1975. I mean, just look at it. It weighed over 8 pounds, it took a grainy 0.01 megapixel black and white photo, and, get this, it took 23 seconds just to save that one image to a cassette tape.
To the device you're probably watching this on right now. A sleek little thing that captures absolutely stunning, high-res images in the blink of an eye and can share them with the entire world in seconds.
You know, this huge transformation didn't happen in one big leap. It was really a series of 4 massive revolutions. We're going to walk through the chemical miracles that first made a picture permanent, then the electronic jump from silver to silicone, the genius architectural redesign of the sensor itself, and finally, the computational wizardry that basically lets software become the lens.
But first, we've got to go back, like way back. See, before photography even existed, the real problem wasn't taking a picture, it was keeping it. For centuries, the idea of capturing an image was this temporary, almost ghostly experience.
The fundamental idea behind every single camera ever made is something called the Camera Obscura, which is just Latin for dark room. And it's not even an invention, it's a totally natural phenomenon. Light streams through a tiny hole into a dark space, and boom, it projects an upside-down image of whatever is outside. The scientist Alhazen was the first to really write it down scientifically, over 1,000 years ago.
And the pace of development was just glacial. I mean, it went from an observation by ancient philosophers to a scientific tool, then a tool for artists. By 1685, Johann Zahn was imagining a portable camera box, but the physics was way ahead of the chemistry. It would take another 140 years for the chemistry to finally catch up.
And that brings us to our first huge revolution, chemistry. This was the breakthrough. It wasn't just about capturing the light anymore. It was about finding a way to make that light stick, to burn that fleeting image onto a surface for good.
So in the 1830s and 40s, you have these two competing ideas. The daguerreotype made these incredibly sharp, beautiful images on a metal plate, but they were one of a kind. The real game changer was the calotype because it introduced the single most important idea for the next 150 years of photography, the negative. And with the negative, you could finally make copies. And this is the guy who took that idea and gave it to absolutely everyone. George Eastman's whole philosophy was about simplicity. His 1888 Kodak camera came with film for 100 pictures already inside. All of a sudden, photography wasn't just for experts in a lab, it was for you, me, everybody.
For almost 100 years, photography meant chemical film. That was it. But the next revolution was about to swap that silver for silicon, and that kicked off an epic battle between 2 different types of electronic sensors. Okay, so we're back to Steven Sasson's crazy contraption. The heart of this thing was a new type of sensor called a charge-coupled device, or a CCD. The best way to think about it is like a perfectly organized bucket brigade. Each pixel gathers some light, creating a little packet of charge, and then passes that packet down the line to be measured. This method was amazing at creating a clean, low-noise signal, which is why CCDs were the champs of the early digital era.
But the CCD had a rival, CMOS. Now, don't get bogged down in these diagrams. The key takeaway is super simple. Early CMOS sensors were just noisy. The images weren't great. But then a team at NASA's Jet Propulsion Lab had this brilliant idea. They stuck a tiny amplifier right onto every single pixel. They called it the active pixel sensor. And that one little change was a revolution. It cut down the noise dramatically and made CMOS a serious contender overnight.
So this is the crucial trade-off. CCDs, they gave you incredible image quality. But they were power hogs, they were slow, and they needed a bunch of extra chips to work. CMOS sensors, on the other hand, were way faster, sipped power, and, this is the big one, they had the potential to put everything on a single chip, a camera on a chip.
And that potential was realized so fast it would make your head spin. What was the driving force? The cell phone. Phones desperately needed small cameras that didn't drain the battery, and that was exactly what CMOS was good at. So the technology just exploded. By 2007, just 14 years after that NASA breakthrough, CMOS had officially taken over the market. So, CMOS won the war. But that wasn't the end of the story. The third big revolution was all about architecture. Engineers started to rethink the physical layout of the sensor itself on a microscopic level to squeeze every last drop of performance out of it. Okay, let's walk through this evolution. At first, we had what's called front-side illumination. The problem was all the metal wiring that makes the sensor work was on top, so it's literally blocking some of the light. The solution was brilliant in its simplicity. Just flip the whole thing over. With back-side illumination, or BSI, the light gets a straight, clear shot. The next big jump was stacked CMOS, where the pixels and the brain of the sensor are built on separate layers and then sandwiched together. That unlocked unbelievable speed. And this number right here really shows you the impact. When Sony introduced the first consumer camera with a BSI sensor back in 2009, they claimed an 8 decibel improvement in signal-to-noise. Now, what that means in plain English is a roughly twofold increase in sensitivity. It's a massive leap, especially in low light, and it immediately became the new standard for every smartphone.
And that brings us right up to the modern day and our final revolution. With the hardware, the sensors, pushing the absolute limits of physics, the new frontier isn't just hardware anymore, it's software. Welcome to the age of computational photography, where algorithms can do things that glass and silicone alone just can't. All the magic your phone does, it's not one thing. It's this whole toolkit of clever tricks. It's not just taking one picture, it's rapidly firing off a bunch of shots and merging them to create one perfect one. It's building a 3D map of the room to fake that blurry background you love. It's stacking frames in near total darkness to see things your own eyes can't. Your phone isn't just taking a picture anymore, it's computing one.
So where does all this go from here? Well, if the entire history of photography up to this point was about collecting as much light as possible in a bucket, the next stage is about something way more precise. It's about counting every single particle of light.
This is the idea behind the quanta image sensor. Instead of pixels, imagine billions of microscopic little dots, each one so sensitive it can detect a single photon. So instead of taking a picture, the camera captures this massive data cloud of where every single photon landed. Then, the final image is built completely in software, which means you could decide things like the brightness or even the resolution after you've already taken the shot. It's wild.
And that brings us to the final thought here. This whole journey from silver to silicon, from collecting light to literally counting it, it's been just extraordinary. But as our cameras stop being passive recorders of the world and start becoming active computers that build an ideal version of it, it leaves us with a pretty fascinating question to chew on. What's it even going to mean to take a real photograph in the future?